So this is our last day of this stuff, like I said. And I guess like all of them, there's sort of different types. There's definitely some commonalities. These ones are a little bit different from the other ones we've done. I mean, they involve trigonometry, so they're different, but there's a lot of different little parts to them. But the same habits are absolutely true, where you want to think about what's changing, think about what's not changing, think about what formula relates the values that you're using, think about the values you need to plug in, think about the values you have and don't have, that you need or don't need maybe. And drawing diagrams is going to be really important for this. You're going to have to draw a diagram for each one of these and label it properly and that kind of stuff to be successful, right? So all those same habits that we've been working on, super, super important. A lighthouse, searchlight, and like visualizing, thinking about what's actually happening here is going to be important. A lighthouse searchlight 315 meters from the shore makes 1 revolution every minute. How fast is the spotlight moving along a wall? So this is the wall. There's the spotlight. When the spot is 425 meters from point P, and point P is the point that is like at a right angle directly across to the searchlight, right? That's the idea there. So this is a right triangle. So can we start labeling things, putting things on here? What can we do? Good. And what else is true about that, Hawa? What do you think? So hold on, picture this. If this is spinning, the top of this lighthouse is spinning, or the light inside or whatever is spinning, that means this arm is rotating that way. Right? There's your rotation. What do you think?
Oh, no, I was going to say that from Theta's spot.
Okay, good. Sure, we can say that. This is 425 meters. Good. What else? What are these habits that I've been talking about? How can we apply them here? I'll ask you directly, what's changing, what's not changing? Zach? Is or isn't? It is changing, that's right. So we have to give it a label, a variable. So I'll call that X. It's definitely changing. What else? Not changing, right. And where is my theta going to go? How fast is it? So 1 revolution every minute is telling us something. It's giving us the rotational speed, in fact. That's what we call that, a rotational speed. Some of these questions give it to us. We're going to do 2 where it gives it to us, and then 2 where we're finding it. Okay? But that's the key, that this is about trigonometry. So when you're doing the test and they're all mixed up and you have to figure out which one's which, it's going to say something about the rotation. It's either going to give it to you or it's going to say how fast is the angle changing. Okay, so this is trig, right? So we know that. But what else is that saying? Where is that angle theta? We'll call it theta. No?
Would it be like always correspond to more
So where do I put theta? Down here at the lighthouse. Yep, think so. That's theta. That's the thing that's the angle that's being created by whatever direction the light is moving. Okay. And we're given d theta by dt. What is theta measured in grade 12? Shiraz? Were you going to say something? No? What's it measured in? Radians. So d theta by dt is in radians, but it's a rate, so it's over time. And what's the time? It says every minute, so let's do that, radians per minute. And what is it? What is 1 revolution per minute? Two pi, very good. 1 full circle, right? Which we know are 360 degrees, which is 2 pi radians. So our rotational speed in this case is 2 pi radians. Rotational speed can be given in different ways, so be aware of that. What if it was half a revolution? Then it'd be pi radians per minute or per second or per hour or whatever. What if it was a quarter? What if it was a tenth? What if it was a 12th or something like that, right? It could be anything. Or it could give you the value, which I think we'll see an example of. Okay, and what are we finding here? How fast is the spotlight moving along the wall? We're going to find dx by dt. And what is the relationship between the change in x and the change in theta? What's the formula? Tan. Tan theta is opposite over adjacent. So tan theta is opposite, which is x because it's changing, over 315 because it is not changing. Very nice. What about that third side in the triangle, the hypotenuse? Could we find it? Could we use that instead? I'm going to give you a tip. You could, possibly, you could, but it would be a lot harder if you're using 2 side lengths that are both changing, like a lot harder. So you don't want to do that. So you always want to be using one side that's not changing, and then the side that is or whatever that you have to use as a variable. So that's a tip that you got to know about the trigonometry ones. If you find yourself using 2 sides that are changing, you're going to have a really hard time. Anybody know what we can do next? Take the derivative. Remember what I said? If you solved one of these questions and you didn't take the derivative and you think you're sneaky, you're like, haha, I found a better way of doing this. No, you found a wrong way of doing it. You have to take the derivative in these at some point. Oh, and what's the derivative of 10? That's a tricky one. We haven't done that in a while. Very nice, secant squared. Secant squared theta. What's the rest? Not x. Nope, not quite. We're missing a few things. So this has dx by dt, because I didn't write it that way, but this is like 1 over 315x. Coefficient is 1 over 315. So it's x to the 1, which is gone, but you have to have the dx by dt. We're missing something else. I left an empty space for it. d theta by dt, which we should know should probably be in there because it was one of the things that we were given that we wrote down over here. And it will be there every time when you're doing these trig ones. So if you do enough of them, you'll, even if you forget it, it's one of those ones that is easy to forget, I think. But hopefully then when you go to start subbing in and solving, you'll recognize what's happening. Before we can finish this question, what are we missing that we need? So we're solving for dx by dt. That's a value. We know d theta by dt. Theta. Even better, what do we actually need? Not theta, but secant of theta. And then we'll square it. Can we find that? What is secant? 1/cos. So cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. We don't know the hypotenuse. Can we find that? H equals the square root of 315 squared plus 425 squared, which works out to a very large number, 279,850. I'm not going to take the square root and round it. The reason why I'm also not finding theta, because I could find theta using tangent, because I have the values. I could do tan theta is 425 over 315, shift tan, like I could do that, but that's going to give me a value that I then have to round or hold in the memory of my calculator. You could do it that way, but if you round, then it's going to be wrong, okay? Because we can do this exact. This is a better way to do it. This is also just a nice trick that we should recognize as something that we can do. We don't have to solve for theta if what we need is secant theta, and we can just get an exact value for secant theta. Because what would that be now? Well, it'll be the adjacent is 315. The hypotenuse is the square root of that big number. So that's secant theta. And that's what I can just sub in place for secant theta. Again, take a look. This is, remember what this is. Secant theta all squared. So if I put that in, 279,850 square root over 315, square that whole thing. D theta by dt is 2 pi. I'm going to move the 315 over, multiply both sides by 315. And that's going to give me dx by dt. That's hard enough that you got to focus carefully when you put it into your calculator. So be mindful of that. Make sure you can practice that. Some people find that very easy, but some people still make little mistakes punching things like that into their calculator. 5,582 meters per minute. That sounds pretty fast. Any questions about that? Would the spotlight be moving faster when it gets closer to point P or further away from point P? When is the spotlight moving fastest? Any ideas? It is faster when it moves farther away, you're right. What are you thinking? And think about what is it approaching? Like, it's approaching parallel to the wall, not touching it, which would be like infinite, right? Eventually, the speed would be infinite when it's about to go parallel, or approaching infinity. So it would be moving insanely fast. So 5,000 meters per minute is because it's fairly far out. If it was closer, it would be quite a bit slower. What else is a little bit different about this question compared to other ones that we've done that I think is important to talk about? Somebody asked a really good question about it in Block A. The question was, which direction is the spotlight moving? We didn't actually say whether that distance was increasing or decreasing. We just said it was moving. Does anybody know the answer to that? What direction is it going? I think everybody has an intuition of just what they think is happening, just in their imagination, but you can't go based on that. Okay, so the answer will be the same, but whether it's positive or negative would possibly make a difference. Negative usually means getting smaller. Why? So the speed that it's moving at doesn't depend on the direction. It would be the same speed whether it's going in or going out at that point, right? Technically speaking, whoops. Oh boy, how am I going to get rid of this now? There we go. Technically speaking, what direction do radians measure? Rotation. They measure them this way. So if we put in positive 2 pi, we're saying it's rotating this way, which means if we get a positive answer, it's going in this direction. But that doesn't actually matter for a question like this. You don't have to worry about it. We're not concerned about that kind of a question. Some of the other examples are going to be, it's going to be obvious. Spotlight questions, we don't really worry about it. The question might say that it's moving towards or moving away, but totally depends on your frame of reference. And honestly, if it said it's moving away from the point, I wouldn't make the rotational speed negative. I would just then interpret it positive as that direction. Like you kind of always just do positive with these ones. That makes sense? I hope it makes sense. If not, we can talk about it more after. Let's try another one. Well, you'll see this one, positive and negative makes sense because it's the balloon rising. So we know that would be positive direction and negative would be the other way. If the balloon was falling, we would make it a negative rate. Okay, so the first one, we had a diagram, you didn't, you had to draw it, but this one I have to draw it as well, so we're going to do that. A balloon rises into the air from a point on the ground 100 meters away from an observer. The angle theta between her line of sight and the ground increases at a rate of 1/20 radians per second. That's not 1/20th of a revolution. That's 1/20 radians. So it's giving us the value. Okay. Find the vertical velocity of the balloon when theta is pi by 4. What makes that special? Theta is pi by 4. Again, last question didn't give us theta. This one does. Just happens to. And so this will play out a little bit differently. I should go back. Because what happened when I talked about it originally, all the little things that we had to do, when we got to this part, we realized we needed secant. So we had to do this to put in there. But when I got to this part, I needed this. So I had to do this to put in there. So like as you go through it, there's all these little things that you have to do along the way. And you either, I guess, get experienced enough that you know you're probably going to have to calculate the hypotenuse, and you know you're probably going to have to find secant of something, or as you're working and you don't have something, then you realize you have to go find it. So this one gives us theta, and it's an exact value. But what is special about pi by 4? Which one? Yeah, so it's isosceles. Remember, one of the triangles comes from isosceles. The other one comes from an equilateral triangle. So I can draw an isosceles triangle here. Well, I can attempt to draw an isosceles triangle here. by making those two lengths the same. That's not bad. So this is my balloon. And the balloon is rising into the air from a point on the ground 100 meters away from an observer. So this is my observer over here. So this is 100 meters. What is relevant about that 100 meters? Not changing. Here's h. This is the speed of the balloon. This is what we're being asked to find. Find the vertical velocity of the balloon. We may or may not need the value here, but we know what it is. What is it? It's 100. It's the isosceles triangle, right? You could either just make that statement, or you could do like tan of pi by 4 equals opposite, which is h, over adjacent, which is 100. And that's gonna, and then this is 1. Tan of pi by 4 is 1. So h is 100. However you end up doing it, you can figure that out. Okay? We're finding dh by dt. The angle theta between her line of sight and the ground, so this is her line of sight, that's the ground, so this is theta. And we're given d theta by dt. It's 1 over 20 radians per second. So again, what's the relationship here? Seema? Look what formula. Tangent again. A lot of these questions are tangent. Not always, but a lot of them are. Okay? It's good to be aware of that, but not all of them. We'll see an example of that. So tan theta, remember, you want to use one thing that's not changing, and then the thing that you're trying to find or whatever, or the thing that you're given. So we're trying to find this, so we have to use that, and I'm going to use this. This is changing, right? This is getting larger. It has to be. So you don't want to use that when you take the derivative. So tan theta is opposite, which is h, over adjacent, which is 100. Take the derivative. And it's like exactly the same as the last one, except a different number. And what are we missing again that we did the last time? Remember? There we are. What did we have to go and find last time when we got to this spot? We did. We actually have h this time. There's no h in here. Why did we find h last time? Actually, we were given. Yeah, we need secant of theta, in other words. So last time we used Pythagorean theorem to find it. And you could do that here as well. Or you could use special triangles, because this is a special triangle. So what do we know about secant of pi by 4? Secant is 1 over cos. What is cos of pi by 4? Zach? 1 over root 2. So this is 1 over root 2, which is root 2. That was easy. That was better than using Pythagorean theorem You would have ended up with a big number that would have just reduced to root 2. Okay, so now we can sub in root 2 squared times d theta by dt, which is 1 over 20, times 100, moving that over, is our dh by dt. 100 divided by 20 is 5. Root 2 squared is 2. 5 times 2 is 10. And I believe that is in meters per second. Therefore, the balloon is rising at 10 meters per second. Any questions about that one? Okay, example number 3. So this one's a little bit different. A helicopter leaves the ground at a point 80 meters from an observer, rises vertically at a rate of 2.5 meters per second. How fast is the angle of elevation of the observer's line of sight to the helicopter increasing when the helicopter is at an altitude of 60 meters? So this one is asking for something different. The first question was the rate of change of the spot on the wall. So that was a changing length. The second one was how fast is the balloon rising? That was a change in height. This one is asking for how fast is the angle of elevation changing. Okay, so it's quite different. Let's see. It's a point on the ground 80 meters out and an altitude of 60. So just to draw this to a moderate degree of scale, you make that line long, that line not as long. And then I'm going to let you start labeling. And thinking about all those little things. What's changing? What's not changing? What are you finding? What's it called, what you're finding? That's what we really need to narrow down. What is it called, the thing that we're finding? So I saw some people do this. Good. Helicopter has an altitude of 60 meters. What does that mean? Height, but it's changing, so I'm going to give it a variable. What else does it tell me about that? Seema? So that we're going to call that dH by dt, right? And it's going up, so it's positive 2.5 meters per second. And where's theta? The angle of elevation of the observer's line of sight. So again, that's going to be here. And we are finding what? Good, d theta by dt. What's the relationship? It's tan again. Opposite and adjacent. See what I mean? It's often tan, not always. And tan theta is h over 80. We need secant. So I'll call this x over here. And in this case, I'm going to use Pythagorean theorem, 60 squared plus 80 squared. And that is, again, a triplet, so it works out to exactly 100. Secant theta is the reciprocal of cosine. Cosine's adjacent over hypotenuse, so secant is hypotenuse over adjacent. We've already talked about that, but again, that's, I think, the way that you want to think about that. The hypotenuse was 100. Adjacent is 80. So that's 10 over 8 or 5 over 4. And this works out to actually exactly 0.02 radians per second. That's what everything was done in. It's measured in radians, so radians per second. Questions? We're good? We're going to do one more together. We're going to skip example 4 from your handout, and I'm going to challenge you to try that one on your own. It's got a bit of a thinking part to it, not calculus thinking, just general problem-solving thinking. You got to kind of, draw it and think about it and just make the connections. I think it's a good one for you to actually struggle through on your own. So you can try that, but I'll post it with the lesson online, and you can look at it, make sure you did it right, or if you just want to look at it. But I would strongly recommend you try it. Okay, this isosceles triangle one. Try it yourself before you look. We're going to skip to example 5. And again, I'm going to say, I want you to start sketching this. There's my wall. So my ladder is 5 meters long and it reaches 3 meters up. So I'm going to do something like this. They're not the same. No, they wouldn't be the same because every time you're subtracting this, you're adding it to those. Yeah, they would be. Okay, tell me something about this. Okay, what did you put so far?
The height is 3 meters, and then dh by dt is 0.5 meters.
Good. So you're telling me it's changing. So I'm going to call it h. It's 3. And what is important about that rate?
Would it be negative if it's sliding down?
Definitely sliding down. Negative 0.5 meters per second. And it is sliding down, isn't it? What's happening to this end? It's sliding out that way, isn't it? How a ladder would fall. Okay. Good. What else? Yeah, okay, good. And I can label that, right? So 5 meters. And I saw a bunch of people make a comment about that. What did you think about that? Not changing. Remember what I said at the very beginning? You got to use one side that's not changing. So the other 3 examples that we did were the diagram is a little bit different. In this case, it's a different side that's not changing. These ladder situations, I guess, can be a bit different. So, what now? Yeah, we can. Oh, so it's a triplet, so we know that last side. So x, is 4 by Pythagorean theorem. You might say like PT, Pythagorean theorem or something, but if you know it's a triplet, it's still by Pythagorean theorem. You just didn't have to do the work. Yeah. What now? Dylan, what do you think our formula is? I think that's a good idea, don't you think? So I used H instead of X. Use something different, but very good. Oh, and we are, where's our theta? How fast is the angle between the ladder and the ground? So I forgot to label that. So there's our theta, and that's why it's sine equals H, or whatever variable you used, over 5. And that's why it's sine. So this one's different. So we're finding d theta by dt, and it's sine theta is h over 5. Derivative of sine is just cos. Don't forget d theta by dt. It's 1 over 5 dh by dt. What is cos theta? Well, we've got the side already because we already found it. If we hadn't, we would have had to do it, but it's just 4 over 5. Adjacent over hypotenuse. Therefore, the angle of elevation is decreasing at 0.125 radians per second.